Welcome to the second video of AP Statistics. We're going to be talking about describing distributions with numbers. In the previous video, it was all about representing data sets with graphs. This one's more about representing data sets with numbers. So the first number we have to talk about is measures of center. And we have two measures that we focus on. The first is the mean, denoted by x bar, which is the average value of your data set. Now, X bar is if you have a sample. You may also see mu used for the mean, but that represents if you have the whole population. So for example, if you want to know the average GPA of your whole school and you had everybody's GPA, that would be the mean of your population. So you'd use mu. But if you only had 10 people's GPA and you average them, that would be a sample of the GPA because it's not the whole group that you're interested in. Now, I think all of you know how to find a mean, which is add all the numbers together, divide by how many numbers you have. But I did want to show you the formula. So if you see it on a formula sheet, you're not like, what the heck is that? This is sigma notation. And if you've never seen sigma notation, the sigma is that uppercase E looking thing. It's the capital sigma Greek letter. And it just means summation. And how it's written is you usually have an index number. So let's say a 1. So I'm going to start at 1 and let's say go to 3. So that just means wherever I have an I replace it with that number and increment it up. So what I'm saying in the one I've drawn is I want the first x, the second x, and the third x, and I want to add them all together. And then if I were to use the formula I have box, I would divide by n, which would give me the mean of my data set. So it's a shorthand way of saying add everything up, and then in this case, divide by the number of points in your data set. All right, so that's mean. Then we have median, which is your middle number. In order to get the median, you have to arrange all your numbers in order from smallest to biggest, and then find the middle number. So in this data set, if I were to do that, I would cross off the numbers in pairs. Then I run into the problem that if I cross those two out, I'd have no numbers left. So the middle number is in between those. I just average them together, and I get the median is 9. So if you have an even number of data points in your data set, you're going to have to average the two middle numbers. If you have an odd number of data points, then you don't have to average because you're left with just one unique number. Now, both of these you're never going to have to do by hand because your calculator will do it for you. So you can just press a button and it'll calculate the mean of your data, the median, and I will post a different video on how to do that. But it's always good to know behind the technology what it's actually calculating. All right, the question next is which one do I use? Mean versus median. Let's start with this pink histogram. If it's skewed to the right, you can see it has less values as you trail off to the right tail. There's a lot of values and you get smaller and smaller numbers of them. So this extreme value up here I circled in red is pulling the mean towards it. And in that case, means are not resistant to large values or outliers. So if you have skewed data, you're going to use a median. If you have symmetric data, you're going to use the mean. So for example, the reason the median is good for skewed data is it only cares about position, not actual value of the data. So let's say I just had the boring numbers 1, 3, 4, 5, 6. 4 is my median. Now if I took the average, I would end up with, let's see, 18. So the average would be 9. And that'd be fine. But if I, let's say, made this top one 6,000, the average would be much more than 9, and the median would still be 4. So that 6,000 doesn't really represent the rest of the data, but it does affect the mean, whereas the median would be unaffected by it. Now, if you have symmetric data, like the bimodal data here, it appears that's approximately symmetric. So the mean and median are going to be very close. So technically you could use either. Later in the course, you'll see we like to use mean and standard deviation because there's a lot of different rules and inferences we can do with that information. So that's why we don't use median for everything, because mean and standard deviation have a special place in statistics. So if you're symmetric, you can use mean. And the purple histogram is perfectly symmetric. So here we know mean equals median. So you technically could use either, but we would probably use mean. All right, measures of spread. So now that we know where the center is, we want to know how spread out the data is. And we never just talk about the center. We talk about the center and spread. You say one, you say the other. You would never say one without the other. And we have three measures of spread. The first one, range. After I say that this time, we'll probably never talk about it again. And the reason is because range is max minus min. So your biggest value minus your smallest value. And again, that's going to be affected by outliers or extreme values and may not be representative of the actual spread of your data. Therefore, we don't actually use that one. What we do use is interquartile range, which is easily calculatable. You just do quartile 3 minus quartile 1 and use that when you're talking about medians. If we're talking about means, we're going to talk about standard deviation and variance. And again, just like x bar, S sub x is for the sample. Oops, that's for the sample. If you're talking about population, it would be a lowercase sigma. It's like an O with a line on top almost. And variance is either shortened vars, usually for if it's a sample, and if it's population, you'll have sigma squared. But sometimes people write S sub x squared as well. So those are used with the means. Again, if you see Greek letters, it's population. If it's our alphabet, it's sample. All right, so let's talk about the harder to calculate first, the standard deviation. So you're going to calculate the mean. That's why it goes together with mean, because it uses the mean. And then we're going to see how far each data point is from the mean. And that's really what standard deviation is telling you. It's telling you the average distance your data set is from the mean. So you take each one, you subtract the mean from it, and now what do we do? If we were just to add all those numbers together, we'd get 0, because you should have an equal number above the mean and an equal number below the mean. So what we do is we square all of these. That's where the square deviations comes from. Square deviations. And we divide by n minus 1 if we're doing a sample. And this is called the variance. Now we don't use this much. What we do use is the square root of the variance, which is the standard deviation. And we're going to do an example out. Now, if we are doing a population, we actually divide just by n. So it depends on if your data set is a sample or population, whether you divide by n or n minus 1. Again, generally we're doing samples, so it's n minus 1. And when you get to using a calculator and we do the one variable statistics and it gives you standard deviations, it will give you both population and sample because it doesn't know if the data you gave it was a sample or population. So it gives you both. They'll be very close together because it's just one value different you're dividing by. And you have to, usually you're going to pick the S sub x one. All right. So next we have how do we calculate this by formula? So just like the uh, mean formula, the standard deviation formula, will be on a formula sheet generally, and it gives you sigma notation, and you're just taking each x value you have, subtracting the mean, squaring them, then adding it to the next x value subtracted from the mean, and divide by n minus 1 and square root. And if this were a population, the only difference is that I will divide by n. Let me erase this so you can see. All right. So now let's do an example so you can actually get a feel for this. So I would, if you think you know the steps, I would pause and try this one out, or we'll step through it together. All right. So step one is we're going to calculate the mean. So we have these dogs and their height at their shoulders. So we got the cute little sausage dog, and it looks like a Rottweiler, some kind of greyhound. So we're going to add these all up and divide by 5 because we got 5 dogs. And we get 394, and we should put millimeters. All right, second step, we're going to take each measurement, subtract the mean from it, and we get these measurements. Now, if you want to just for your own sake, add all these numbers up, you should get 0. So, because these are the deviations from the mean. So there's an equal number of negative ones, like the negative 224 and the negative 94, and then you have all the positives. So they should add up and cancel each other out around the mean. And that's why we have to square these next. So next we square them, and I'm dividing by 4 now because it's sample size minus 1. Since this is a sample of dogs, it's not all dogs. So I square them each, divide by 4, and so this would be millimeters squared. All right, and then lastly, if I want standard deviation, I'm going to just square root that, and I have dot, dot, dot because decimal goes on forever. I just rounded to the hundredths. And that would be my standard deviation. And I would compare that, use that with the mean. I would say the mean is whatever it was, and then this is the standard deviation. All right, now we already said with median we're doing IQR, and IQR is a simple calculation. So I just wanted to go through making a box plot. Is you'd have your 5-number summary, and a lot of times you'll see questions that'll state, with this data set, give me the 5-number summary. It just means the min, Q1, Q2, or the median, they're the same thing, Q3, and the max. So some people refer to this as Q2. And these will help you make a box plot. So we have our Q1, Q2, Q3, max, min. So if I wanted the IQR, I would just do 91 minus 74, and I would get 17. Right. So that's easy, not as nearly as involved as the standard deviation. But what we can use this for now is to say, do we have an outlier? So is this 45 an outlier? Because looking at the box and whisker, that first whisker is kind of long. So we want to say, do a rule to see if it actually is. It's called the 1.5 IQR rule. It's a very creative name for it because we take the IQR and multiply it by 1.5. All right, so the IQR is 50% of the data, just Q3 minus Q1, and then I take that, multiply it by 1.5, and I'm going to do Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. These are like my fences, and any data points that fall outside of that are outliers. We can say they are outliers. Now, you might be asking yourself, why 1.5? Now, I don't know if this is 100% true, but I found this somewhere that according to John Tukey, 1 IQR seemed too little and 2 IQR seemed too much, so 1.5. 1.5 now is the standard people use, so it's statistically a standard. All right, so we got this lovely Box and Worcester plot again and the IQR. So then I do 1.5 times the 17 and I get 25.5. And then I do Q1 minus that and I get 48.5. So right around here. So that means this 45 is indeed an outlier. And then Q3 plus 1.5 IQR is 116. So that's way over here. So that is not an outlier on that end. 98 is not an outlier. So we do have one outlier. And when you go to graph these on your calculator, which I will also post another video on how to graph box and whiskers on your calculator, you can do it with or without an outlier in it, and most statistical programs will allow you to do that. Generally, we're going to plot them with the outlier still in the data set and then pull it out afterwards and just refer to it as an outlier. But sometimes you will see box and whiskers plotted and the outliers marked as either dots or X's. All right, so that is all for this video, and I hope you enjoyed it.